Welcome back to ECE 442-542. This is a special section, or session, I should say, not a special section. This is a special session of the class, and we're going to be reviewing exam number 1. And first, let's just talk about the process. And one thing that I want to make clear is there is practice material on D2L. Some people are saying, can you give us some sample problems? I would strongly encourage you to start looking at and working some of the problems on the sample exams. That is a separate module in D2L, exam number 1 material. So make sure that you gain access to that or you see it. But in some of those exams, you might see this material printed on the front. You will be allowed 1 sheet of notes for the exam, and that can include both the front and back. It is restricted to being 8.5 inches by 11 inches. It's not unbounded. This is a bounded sheet of notes. So if we're comparing this to the Z-plane, this is a bounded sheet of notes, 8.5 inches by 11. You can bring, and I would encourage you to bring, the Z-transform table from D2L. Now that you've done some of these Z-transforms, you can use the transform pair. You don't have to always explicitly derive these relationships. So now after you've completed homework number 2, if you now see a standard exponentially damped cosine or a standard exponentially damped sine, you just identify the radius and the angle, and boom, you can write down the result, or for the Z-transform. That's what the table is for. Calculators, you can bring up to these, HP 51, a TI Inspire, a TI 89, something to write with. I don't want you to have to write with blood. So a pen or pencil. And if you write something down, I would suggest you just exit out and don't erase it. It might actually have been correct. And then you go, oh, I erased it. Now I have to go back and rewrite. Just say, please grade what I've crossed out. That's fine. Or if you realize it is incorrect, you can say, do not grade what's X'd out or crossed out. You're not allowed a computer, you're not allowed your cell phone, you're not allowed textbook, and you're not allowed class notes. You have 1 page of notes. Yes?
Are we allowed friends?
No, and so this should be, you have to bring your friends maybe, but no neighbors. And we may have enough room to where we can sort of space you out. Not all the way, but some, a little bit. Questions on the process? I'm going to lose my voice and then we'll be done. This will be a quick review, huh? Topics. There is a list of topics in that module in D2L. And in fact, it's right here. Background, you need to be able to do Laplace transforms. You need to be comfortable with modeling. Mostly electrical and maybe electromechanical. But then do Z-transforms, do the complex mapping, and can you solve difference equations? We're going to go through that now in terms of some of that. Practice exams. People have asked, will the problems be similar to homework 1 and homework 2? My quick answer is probably not. No. The homework problems are getting you ready for the exams. The exams problems may not be as lengthy as the homework problems. That's why I'm strongly encouraging you to look at the practice exams. Look at the type of problems on the practice exam. Homework 1 and homework 2, for example, you derived the complex exponential or exponentially damped sinusoid. Now you can just use that. So the homeworks are getting you ready to be able to quickly work through the problems on the exam. And the material from the lectures is through, oh great, what was last Wednesday, date-wise? Do you remember? Oh, no, we were doing through Monday, so it's the 2s and the 1s. It's 2, 10, 20. Through Monday, that was when that material is fair game for exam number 1. The 12th, that you've learned a little bit more, and you can use that insight based on today's lecture for maybe finding the Z-transform in its region of convergence. You didn't know we were, well, we have to. You had to know this. We're in the dance building, or a building that involves dance. We are square dancing here. You need to be able to move around this chart. Difference equations. You need to be able to go from there to transfer function, or difference equations to a block diagram, or block diagram to a state space, or state space to transfer function. This diagram, you need to understand and be able to use it to get from any point on that square to any other point. You may not be able to directly go, but you can navigate. For example, you could start with difference equations, which we will do, I hope, in a little bit, and build a block diagram, an all-delay block diagram corresponding to a difference equation. We can then find the state space representation by labeling the outputs of those delay blocks as state variables. Then we have a state space representation. We could directly Z-transform the difference equations to get a transfer function. If you thought you had a lot of time, I guess you could go to block diagram to state space and then do that formula to get to a transfer function. I wouldn't recommend it if you're starting with the difference equation. But you might be asked, here's a difference equation, give me a state space representation. That you might have to do. You need to be able to solve or find solutions to difference equations. What does that mean? Well, you could have a homogeneous equation with non-zero initial conditions. You might have a non-homogeneous equation, meaning you have non-zero forcing terms. And you could have that with initial conditions. I might ask you for simply the structure of the response. By that I mean you need to identify what's the frequency of the cosine, what's the exponential damping or the weighting, but the coefficients on those terms I don't need you to find or to evaluate if I'm just asking for structure. I might give you a transfer function and a forcing function and say, what's the structure of the output? That you should be able to do without multiplying it out and doing the complete inverse Z-transform. That's what I want you to get comfortable with, and I think we'll go through a little bit of that in a minute, is the plan. Here, and I did receive some quiz responses. I asked you if you had questions for the review session. Please provide me with what you would like to see reviewed in the review session, and I got 18 of those. So I'm trying to hit on some of those. One of the ones that people ask a fair amount on was, how do we find the sample period? Well, here's kind of a busy slide, but you need to understand this and how to use it. The sampling frequency, omega sub s, in radians per second, is related to the sampling frequency in hertz or cycles per second by this scaling factor of 2 pi. That then also, once you know the sample frequency in hertz or cycles per second, you could actually rewrite that in terms of the sample period, capital T. You know those two are reciprocally related. Now you have an expression that relates the sample frequency in radians per second to the sample period, and it's just omega sub s is 2 pi over T. That expression now can be used to help you select capital T. Suppose somebody says, or maybe you're given a transfer function and they say, what's the sample period? Or maybe you're given a circuit, an electrical circuit, and you're now asked, tell me what is the sample period, capital T, if you want to find a discrete, or you want to now discretize the natural response of that circuit. You would then need to find the transfer function of that circuit, identify the poles, find the fastest pole. That's what we're going to agree to in this class. Find the fastest pole. That's omega sub c. That's the closed loop bandwidth. You now scale that by 30. That's our rule of thumb. And then set that equal to 2 pi over capital T and solve for capital T. That would be your sample sample period. If you needed your sample frequency, that's just 30 times omega c. If it was in radians per second, your sample frequency. Are there questions on that picture? Let's now connect that to, let's say I now give you a S-domain figure or plane, and that plane now contains x's. Those x's represent poles. And this particular distance right here, let me keep maybe consistent, this distance to the origin from pole at S sub 1 is a distance R sub 1. S sub 2 is a distance away. That's the hypotenuse that pole S sub 2 is away from the origin. That's R sub 2. S sub 3 has a distance away from the origin of R sub 3. Those are the natural frequencies of those poles, R1, R2, and R3. Which of those poles or set of poles represent the dominant pole or poles? S1 is the dominant pole. Is everybody clear on that? This is now the dominant pole, which means, is that the slowest or the fastest pole? So now I need you to be thinking, if you're at home and raising your hand, you can look at a mirror to see your response. Is that the slowest pole or the fastest pole? Fastest, raise your hand if you think that's the fastest pole. It's actually the dominant pole, which means it dominates the response. That's the slowest pole. Plug in hypothetical values for S1 and S3. Just rotate that S3 down to the real value. This is now the slow pole. And the reason is, let's say that S1 was equal to -1. And let's say S3 or R3 is, well, it's just a magnitude. Let's say it's 10. So now this would be e to the minus 10t, and this is e to the minus t. Which of those is fastest? Which disappears the quickest? Do you see that this is the fastest mode of those three sets? It's the furthest away. This is the fastest. And which of those would you use for omega c? Do you see the distinction between slowest and fastest now? I don't care if you got it wrong tonight. I just want you to get it right in a week. All right? If you got it wrong tonight, based on our learning, now you'll never get it wrong again, maybe. Right? About our understanding of learning. Which of these do we use for omega c? That's the next question. We've identified, is it clear which one's slow and which one's fast and why? Question. What happened to the vertical distance?
So you said, is it clear if it's the same way? Why is it the fast? Can you explain the E part?
So why is it, okay, so now it's not clear is the question, I think. It's not clear why the S sub 3 poles are the fastest and the S sub 1 pole is the slowest. Do you see that S2 is between those?
Yes.
Okay. So now we're measuring speed now. This is kind of our inside class here. We're just measuring speed by the distance those poles are away from the origin. And the further they are away from the origin, the faster they are. Because if we rotated that S3, those S3 poles down to the real axis, do you see they would be a distance of R3 into the left half plane? So let's just say that that ends up being at minus 10. Then if you inverse Laplace transformed a pole at minus 10, that corresponds to e to the minus 10t. The one at S1, we said, let's just hypothetically say that's at minus 1. That is a pole at s equal to minus 1. That inverse Laplace transforms to e to the minus t. Now, plug in values of t, and I hope you can see that e to the minus t doesn't decay exponentially as fast as e to the minus 10t. So at t equal to 1, the S1 pole is at e to the minus 1, 0.37. The pole at s sub 3 is at e to the minus 10. I don't even want to know what that is, but that's much less than 0.01. E to the minus 5 is less than 0.01. Do you see how that one really decays quickly? It's the fastest. So now, is it clear now why S3 is the fastest of those sets of poles? And why S sub 1 is the slowest, and that one dominates the response. The poles at S3, boom, they're gone in a blink, and the dominant behavior is determined by S1. That's the slowest. Question?
Yeah, so just to confirm, the dominant pole is always the one that's closest.
Just as a confirmation, the dominant pole is the pole and closest to the origin. Yes. In this class, we're going to agree that we'll just focus on one pole. In fact, if we had a cluster of poles at S1 and S2 was just a little bit to the side of it, they would help each other. But we're just going to say, for simplicity, let's just deal with the one nearest the origin. That's the dominant. Okay? In practice, they all play together and they do help each other. But we're going to just say, to make it cleaner, let's just talk about a fast and a slow. We clear on that distinction of fast and slow. If that's the case, what do we choose for omega c? I'm trying to find a sampling frequency or a sample period. I need to know what is omega c. And here we're assuming R1 is less than R2 is less than R3. What is omega c? What do we use? We use the magnitude of S sub 3. We use its distance away, its natural frequency. That's now the magnitude of S sub 3. And I called that sigma sub minus sigma sub 3 plus j omega sub d3. So this now is what we would do. We would take the square root of the real part squared plus the imaginary part squared and square root that. We just find the hypotenuse of those, and that's what we are going to agree to call the natural frequency of all of those poles, and the one that was the fastest was associated with S sub 3. That's what we use to determine our sampling frequency. We need to base that on the fastest oscillation in the system. Show me up here. Which one are you talking about? Yes, so omega sub c is S sub 3. My writing may be very muddled, but I think that's a 3 for a subscript. So if you're looking at a distant screen, it may look pretty poor. But I think that's S sub 3. Is that okay? Okay. You were really making me nervous. Because this is why I usually make my S's like that, because when I started looking at that, I thought, what's omega 5 doing up here? But that was omega sub S. Yes.
So we'll always choose omega c as the natural frequency of the fastest pole?
Yes. So the question was, or comment was, we'll always choose omega c to be the natural frequency of the fastest pole. And the fastest pole is the one furthest away from the origin. So we're just agreeing that's going to be what's defining our omega c. Now you know how to pick the sample period. I hope. Is that clear? And now you could find those poles from a circuit, from a mechanical system, etc. Or I could simply draw a diagram and say, here's your S-plane. How are you going to sample this? You could now find capital T. Stability. Oh, and remind me, if it gets to be 11 or something, you might tell me it's getting late. Okay. I think I've already gone beyond the threshold of hunger, so hunger's not going to be a factor. I'm already starving, so it doesn't matter. BIBO stable. Bounded input, bounded output stability. The system, H of Z, for it to be bounded input, bounded output stable, has all of its poles blank the unit circle. I feel like I'm on a game show. Jeopardy. I'm not going to pay you for answering this, but do you remember, or what is your answer? Inside the unit circle. And here is a picture of different scenarios. There's a system on the left, and I've tried to indicate the unit circle. The unit circle is just that circle that's a distance 1 from the origin. So if I say unit disk, then that's the whole thing, but I'm saying unit circle. Okay? The the system on the left has all these x's relative to the unit circle. The system on the right, I have two different systems. I hope that's clear. One on the left, one on the right. Can you tell me about the stability of those two? The one on the left, is that stable or unstable? The system on the right, it only takes one pole outside the unit circle to destroy everything. All you need is one pole outside the unit circle and your entire system is unstable. That, I hope, is clear. Yes?
How can we relate bounded and unbounded to stable and unstable?
So bounded and unbounded is related to stable and unstable. Where I'm confusing you is talking about the region of convergence. So the region of convergence is disconnected. That discussion is independent of stable and unstable responses. So stable and unstable time domain responses is disconnected. I mean, they're related, but they're not. Okay, those are independent concepts. If we have an unbounded region of convergence, that just means the region of convergence, the z-plane, is going off to infinity. That has no, that's independent. I shouldn't say it has no connection. That is independent of whether your time domain sequence is bounded or unbounded. So now when I say bounded input, bounded output, I just mean I put in a bounded sine wave or a bounded cosine wave. I shake the system with a bounded input. Is the output going to remain bounded? That's what I mean. Is the waveform, are all the waveforms in that system going to, or in the output, is the output going to be bounded? If I actually put a pole here at 1, is that system bounded input, bounded output stable? I could now actually apply a unit step, a constant input, to a system that has a pole at z equal to 1, and that output is going to go up as n increases. So you need all of your poles to remain off the unit circle to maintain bounded input, bounded output stability. You can't have any poles on the unit circle. If you do, I can hand you a sinusoidal waveform that will shake that system just right, and your output will go unstable. All the poles need, so I have to erase that, don't I? Or this is going to get really confusing. Who knows if this is going to work, but let's, well, it's close. Okay, we're back to, I think, where we were, to maintain that being stable. So if that's not clear, what I would recommend you do is get a system and just say h of z is 1 over z minus 1. Apply a unit step to that, and then see what the output does. Inverse z transform h of z times u of z, and see what happens. You'll get something that's going unbounded with little n in the time domain. I know this is making some of the students uncomfortable that are coming maybe from a mechanical background, but you need to make sure you can analyze a circuit that's maybe first or second order. Yes?
Before you move on, if you have like a state space representation, can you directly say from that if the system is stable, or you have to go through to get your transfer function?
So now if you have a state space representation, how do you assess stability? You then need to look at your system matrix. Did we call that phi, capital Phi, I think, in discrete time? You find the eigenvalues of that system matrix, which would correspond to the poles of a transfer function. I would not find the transfer function unless it's quick and clean. I would just find the eigenvalues of that system matrix. If those are all having magnitudes less than 1, your system is bounded input, bounded output stable. Okay? Equations of motion. You should be able to write Ohm's law, KCL, and KVL in such a way that you could find a transfer function for a first or second order circuit. Because in some of the problems on practice exams, I'm thinking one might be, what's the sample period for this electrical circuit? And you're going, this is an analog circuit. But I'm asking, what would allow you to obtain a reasonable sample signal or waveform from that circuit. Now you would find its transfer function. Let's say it's 2 poles. What do? Now you know what to do. You would plot those and say which one is the furthest end to the left half plane. That's now my omega c. I sample 30 times that. That's my omega sub s. If I need to know capital T, I can find that by 2 pi over cap T. And I don't think you're going to have time to take a circuit and, well, yeah. I'll stitch problems together to where I'll try to test you on different ways. For example, I could give you a differential equation and say, what's a difference equation for this? But we'll have plenty of time to do discrete equivalence at later sections in the class. So I don't think that's going to be the focus of exam number 1. Z-transform. Here's the focus for exam number 1, is up here in the right-hand corner here. And now maybe that makes more sense to you after today's lecture. We want causal sequences, x of n's, that have non-zero values for positive or non-negative values of little n. That's probably what I'll be asking you to z-transform. And those region of convergences are all beyond the largest pole in that system, or in that transform expression for little x of n. For exam 2, that's when we'll start asking you about different regions of convergence, etc. Here, can you find the z-transform for a waveform? Can you do it for a difference equation? If I gave you this difference equation, can you z-transform it? And typically I would be asking you to find a transfer function, and that makes it even easier, because what does that mean? What can you neglect if I'm wanting a transfer function between u and y? You don't have to worry about initial conditions. You can just replace alpha 1 y of n minus 1 with its z-domain expression, which is alpha 1 z to the minus 1 capital Y of z. And if I want a transfer function between the input u and the output y, what does that look like? Or what is that? And this question was asked in one of the discussion questions in D2L, but that now says you're looking for y over u, not u over y. I'm wanting the transfer function between the input u and the output y. H of z is then y over u. Because when you now multiply this by u of z, you better get y of z. You better get the output. If I give you an all delay block diagram, I hope you know it's trivial to find the z-domain or the frequency domain version of that block diagram. You simply erase the delay operator in the time domain and replace it with a z to the minus 1 operator. What you also, I would want you to I would want you to do is capitalize your signals. And if you put an argument, it's now capital U of Z, or capital R of Z, and capital Y of Z. I don't want you mixing time domain and frequency domain. You now should be able to find the transfer function from these different representations. If you're given a block diagram, hopefully you can do some block diagram algebra to find the transfer function. If I give you a difference equation, that one's probably the most straightforward to find the transfer function. You can neglect initial conditions when you transform, take the ratio, and you're done. State space, that takes a little bit more mathematical machinery or process, but you simply plug in the appropriate matrices into this form and you have your transfer function. And if you're running out of time, I would identify phi, gamma, h, and j and say, here it is, and write down that expression. And then move on and say, let me work some more and I'll come back and do the inverse of zi minus phi if I have time. Yes?
Can you give us a problem on the exam that's similar to problem 3 and all when we separate the two, W, Z?
So now the question was, will I give you a problem on the exam similar to one of the problems on homework 2? Was that homework problem 3 on homework 2? Yes. I may, and I'm going to work through one of those that I hope will make you feel a little bit more comfortable with that process. I'm going to do it a little differently today. And you can look at the... So the reason why it was confusing is because we now had delays in the input. And because we had delays in the input, that's why I went through all of this explanation for why in the world is he introducing a new variable, capital W, into this. Well, I was trying to separate that into 2 steps. One step to find a block diagram from U to W, and then find the connections to relate the output to the W's and delayed versions of those W's. We'll try to get through a different way of looking at that, starting with coupled difference equations and creating a block diagram, and then maybe generating a state space representation from that. That's the goal. What if I now want you to find the settling time? Here is the z-plane, and I have 2 pairs of poles. I have one pair, and they're a distance capital R sub 2 away from the origin. And I have another pair, and they are a distance R sub 1. Now, if I'm asking for settling time, when does that question even make sense? Or what fact has to be true for me to even be asking that question? It has to settle, which means what? That means all of those x's better be inside the unit circle, which I think you can see they are based on 1 and minus 1. Those x's need to be inside the unit circle. If one of them is outside, you can say, ha, this doesn't settle. No settling time exists. If you had a pole at 3/2, no settling time there. It's just going to go unbounded. Z-plane. Where are my dominant poles? I have this pair and I have this pair. I want to know yellow or blue. I hope those aren't very clear, but which one dominates, yellow or blue? I want to see hands if you think it's yellow. That dominates, huh? It doesn't. So it's kind of the opposite in the z-plane. Which of these are the fastest? Remember, you're R1 to the n, right? And R2 to the n. R1 to the n is bigger, and it collapses more slowly than R sub 2 to the n. Just put some numbers on this. Say R1 is, I don't want to do this because I don't want to do the math, but let's say R sub 1 is 1/2, and let's say R sub 2 is 1/4. Now you have 1/2, 1/2 squared, 1/2 cubed. That's shrinking slower than 1/4, 1/4 squared, 1/4 cubed. You now have 1 over 4, 1 over 16, 1 over 64, compared to 1 over 2, 1 over 4, 1 over 8. Do you see that the poles at R sub 1 are slower and they dominate the response? Plug in numbers, but here the dominant poles are the poles that are closest to z equal 1. The poles that are closest, in fact, to the unit circle. These are the dominant or the slowest poles. And this, why did I mix up my colors? So I'll not. This is the fast. So which one of those, R1 or R2, do you use to determine settling time? Which R? R2 or R1? We want settling time. Settling time is determined by the fastest or the slowest, the settling time. It's the slowest that determines the settling time, because the fast one's going to settle quick, and the slow is coming in slower. You use the dominant, the slowest pole, to determine settling time. So which R? It's R1. And now you would just plug R1 in to that expression, and now you're really looking at R to the n, or R1 to the n, equal 0.01. Solve that for n if you need to now find the number of sample periods for that to settle. And that involves a little logarithmic solution. Take the log of both sides, base 10. And you can then solve that for capital N, which is, I might call that N sub S, for the settling, the number of samples to settle within 1%. Are we clear on that, and why? Why are R1 poles dominant versus R2? Just plug in some quick numbers to convince yourself which ones are dominant, and then why is the dominant one the one that you use for settling time. That one dominates the response. That's the one that you're going to see the longest. That's the one you have to use to determine your settling time. As promised. This is from spring of 18, so not last year. I think I was nice or something last spring. I didn't give them this kind of a problem. So be prepared. Find a state space representation for this coupled set of linear difference equations. And this is coming from, and if it's not, you can correct me, but it's coming from an old exam, and I think it's coming from the spring of 18 exam. You have all sorts of exams in the exam number 2 material module to practice. And what I would suggest, there's some that don't have any answers. I would work through those, try to work through those before you look at the ones that have the solutions. Yes? So now, wouldn't we just plug this right in? What are we wanting? We want x at time n plus 1 to equal some linear combination of x's at time n plus u's at time n. Now, looking at this, you might be tempted to say, well, this is just a standard state space. I have W1, that's like X1. I have W2, that's like X sub 2. But if you look on the right, you see that what makes up W1 and W2 is not just W1 and W2 at time n and U at time n. It's in fact subsequent delays beyond that. So this is not immediately writable in a state space form. And these are kind of coupled. We have W1s and W2s and U's sprinkled on both sides. And the output, Y, is just what I've defined it to be. Somebody, I think, in their question said, where did the output come from? A lot of times it just comes from me creating it. I just built the output here and I said it's 5W1 minus W2. Add in. Okay? That's why. And if you need to get up and stretch, please do. I get to walk around a little. But I've been walking around now for a few hours, so I might be sitting down in a minute. I better not. Better stay on my feet. How do we begin? Well, what we are doing now is we assume that we have these variables, W1 and W2 and U, at the time instant, little n. We're assuming we have those available. And that's going to now allow us to sketch a block diagram. How is that possible? Well, first, I'm going to do just a quick rewrite of these top two equations. I'm going to write those in terms of W1 of n and W2 of n. I'm assuming I have W1 of n and W2 of n. I'm going to say, oh, the top one, I'm going to replace the left-hand side argument with n. What does that mean I have to do with the terms on the right? I just lower them each by 1. And they still maintain the same relationship relative to nearby samples. Is it clear what I'm wanting to do? I want to rewrite that first equation as W1 of n equals 0.5 W1 of what? N minus 1. Since I reduced the argument by 1 on the left, I have to reduce the argument of everything on the right by 1. My W1 equation now, and this I hope will make sense as we get into this, but now I'm going to say I want W1 of n is equal to 0.5 W1 of n minus 1 plus W2 of what? N minus 2 plus two of U of n minus 2. Everybody comfortable with that? The same relationship in time between those variables. I'm going to do something similar with W2 of n. W2 of n is now W1 of n minus 1 minus 4 W2 of n minus 1 plus 3 U of n minus 1. Everybody okay with what I've just done? I've simply rewritten those first two equations in terms of the highest argument being n. And I've put that highest argument on the left. I could give you a difference equation with terms on the left and the right. Now what I'm saying is solve for the highest index and put that on the left and then rewrite it as n for your highest index. Now, what am I going to do? Well, I need to somehow accommodate these delays of more than one. What I'm going to do now is I'm going to rewrite in the time domain u of n minus 1, d is my delay operator. I'm going to say that is that. D is an operator. It's like a drawer. You stick a signal in it, and you wait one time interval, and then you pull it out. So one delay of u of n is u of n minus 1. If you had u at 10, one delay of that would have been u of 9. What if I now said u of n minus 2? I'm going to nest these delays. I'm going to say, oh, that's just a delay, and then another delay of u of n. Those are different brackets. If that's scaring you, that's just a different bracket. I guess I could have done this, but I don't want you to think that I'm trying to z-transform anything. This is just a different bracket. So let me change it back. I kind of like that if I could draw it. Are we comfortable with that? Now I'm going, so this is just nesting delays. I want to now use that to rewrite W1 of n in terms of W1 of n, W2 of n, and U of n with delays. Meaning, W1 of n is going to be a single delay of 0.5 W1 of n. Is that believable? Now, how do I get W2 of n minus 2? And I have U of n minus 2. I'm going to put those both inside a second delay. I'm nesting my delays. I already have one delay on the left. If I introduce one more delay, I now have W2 of n plus 2 U of n. So W2 of n is actually experiencing 2 delays before it gets to W1 of n. And that's what I needed in W2 of n minus 2. Can you now do that for W2 of n? This one actually is not as involved because they're all at n minus 1. I just need one delay for this one. This is now a delay, and I have W1 of n minus 4 W2 of n plus 3 U of n. All of this equation now, I hope you see, is made up of W1 at time n and only W1 at time n with delay operators, and that's what's going to be in our all delay block diagram. W2 of n and U of n. Those are the only signals present, but they have to be passed through delays. Now I want to build my all delay block diagram from these two equations. So I'm assuming I have W1 available, U of n available, and W2 available. W1 of n, and now you don't really know going into this where you need to put things, but after you've done it, you can redraw it, but on an exam, you're not going to have time. But now let me put W1 of n there. And in fact, that is made up of a combination. It's the output of a delay block. Do you see that? So this W1 of n is equal to, what that's equal to is the output of a delay block. That's the D. And what's the input of the delay block? That's all of this. So now that delay block needs to have, as its, here's the input to that delay block is the output of that summing junction. And this now needs to be 0.5 W1 of n. What else is it? Well, it's another, and then I need the next signal to actually be another delay block's output. And now I've reached this point. And what's the input to that delay block? The input to that delay block is what's inside those weird brackets. It's W2 of n. So here's W2 of n. And 2 times U of n. And I said I had these signals available. There's U of n, and I'm going to scale it by 2. And that's my first equation. But I have to now define W2 based on the second equation. W2 is the output of a delay block. And what's the input to that delay block? Well, it's minus, if this is W2 of n, it was minus 4 of this. Do you see my signals are actually going in the other direction? It was minus 4 of W2 of n, and that's what is right here. This is now W2 of n. It was also W1 of n, so I can pull W1 of n and put that here. And I need to take this input U and scale it by 3. And that's now built up W2 of n. What was Y of n? Y of n was actually 5 W1s. Let me put this right here, W1 of n. It was 5 W1s and minus W2. So it's going to be a little bit ugly, but mine's in blue, so you can kind of see that this is now coming here. And let me go ahead and, put my minus 1 there. And all of those, unfortunately for you, I have an infinitely wide piece of paper. There's Y of n. Do you see where that block diagram, how you built it? I would suggest you go through a couple of these on your own, but now, how do you get a state space representation from this? What's the strategy? What's the order of the state space representation, just looking at this block diagram? You're now counting delay blocks, and you have 3 of those. It's third order. How do you build a state space representation from an all delay block diagram?
Different question. Could you have started with W2 instead of W1, and then?
I could have started with W2. No, your interconnection would be exactly the same. You could have started with W2. You would have assumed you had W1 and U, and you would have exactly this same structure. You might not have put them on the paper the same, but you would all be interconnected exactly the same. So you could have started with the second equation and then built up the first equation after that. And you would still get exactly this same structure. Now the state space representation, I might have many different ones, because how do you build a state space representation from this block diagram?
Every time you see a delay coming out, that's like an X, like event.
So every output of every delay block is a state variable component. I'm going to try to be consistent with my notes, and that means that I'm going to label this output as x sub 1 of n. That's one state variable component. The next one is going to be the output of this delay block, x sub 2 of n. And the last is going to be the output of the third. And here, remember where the input and the output, that's determined by the arrow directions. There's x sub 3 of n. And now that I've defined my state variables, this input to that delay block is x sub 1 of n plus 1. The input to this delay block is x sub 2 of n plus 1. And the input to this delay block is x sub 3 of n plus 1. Now I'm good to go. I can write x1 of n plus my state vector, which is now x1 of n plus 1, x sub 2 of n plus 1, x sub 3 of n plus 1, equals some matrix times x1 of n, x2 of n, x3 of n, plus some matrix u of n. And I simply look at the outputs of those summing junctions, which are labeled as the appropriate state variables at a certain time, n plus 1, and how do I combine the states at the present time and the inputs at the present time to produce those states at time n plus 1. x1 of n plus 1, what does it equal? I don't have any x sub 3 directly making up x sub 1 of n plus 1, and I do not have u directly connecting into that summing junction. I simply look at all the arrows coming in to that summing junction, and that equals what's going out, and what's going out is x sub 1 of n plus 1. X sub 2 of n plus 1. And don't get confused by the blue. That's leaving that signal to create the output. How many non-zero terms do I expect creating x sub 2 of n plus 1? 2 inputs, and they may not all be in the system matrix. I have a 2 coming in from U, and I have a W2, which was actually x sub 3. That's now x sub 2 of n plus 1. What's x sub 3 of n plus 1? A negative 1, I don't see a negative 1. It's just x1, isn't it? Without a minus, just a x sub 1. And then a minus 4x3. No x sub 2, was there? And then a 3, scaling the input. And what's my output? That was 5 x1s, x3, and no x2s. Oh, that was a minus x3, and there was no direct feed through from the input. This now gives me my phi matrix, my gamma matrix, my output matrix H, and my direct feed-through matrix J. And if I really needed to, I don't know that this would be very fun, but I could find my transfer function. This is now H, Zi minus phi, inverse, gamma plus J. I would now have to symbolically invert a 3 by 3 matrix. But it could be done. Yes?
Sorry, can you go over how you got H? Because I think it has something to do with what you defined Y as N.
So H was determined by how I had originally defined the output, and that was way back here. I said Y is 5W1 minus W2.
So wouldn't there be like 5 negative 1 0 because there's no.
So now W1 and W2 are not the same as X1 and X2. So I actually have labeled W2 to be equal to X sub 3 in my diagram. W2 and W1 now you could actually kind of erase relative to your state space representation, unless somebody needs those. They are no longer needed. You now have created X1, X2, and X3 in this block diagram. Is the system stable? How would you determine? You would look for the eigenvalues of phi. I'm not going to do that here because it's third order. And you would want those to have a magnitude less than 1. What if I gave you another problem? And I don't even know where this came from, so I don't know if it's from an old exam, but let me see how quickly, oh my. I've got about 12 more sheets of notes. I wasn't kidding when I said 11 o'clock. Do we want to do another block diagram or do we want to go on? Yes.
So in one of your sample exams, you had a block diagram and you said to find the closed form structure of the complete solution of Y of N.
Okay, so there, let's look at a closed form solution structure or something. Suppose that we now, well, I did suppose we had this. Suppose we had y of n is equal to 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus 1/2 u of n minus 2. What if I now said, what if you apply if u of n is equal to 0.7 n cosine of pi over 8 n for n greater than or equal to 0, what is the structure of y of n? How would you approach this problem?
Euler's version of cosine.
So now would we need to worry about Euler and cosine? What is the structure of y of n? We now have a forcing function. And what else do we know? We have a system. That system naturally shakes, has natural modes, determined by what? How would we find the way this system naturally likes to shake? The system is given by a difference equation. How do we find its natural modes? If we found the transfer function, we could then find the poles of that transfer function, and that gives us our natural shaking of the system. We're then shaking it with this cosine. Do you see that the structure is going to be a combination of the cosine and the natural modes? That's our process. We need to find the transfer function of this difference equation, find its poles. That will then tell us what our structure of the homogeneous solution looks like, or the natural solution. What's the solution of the particular? What's the particular solution structure going to look like? Can you tell me right away with what's on the board? How am I shaking this? With theta n, where theta is pi over 8 n. If this gets to a sinusoidal steady state, which it will if that system is stable, it will reach a sinusoidal steady state. And how will it shake? With a cosine of pi. Well, this is an exponentially damped, isn't it? So now you're going to have an exponentially damped cosine at that frequency and an exponentially damped sine at that frequency, in addition to the modes that are natural to that system. So to find the structure of y of n, wow, I'm going to do this in 2 minutes. I would first find the transfer function. So I would z-transform that difference equation, and I would have 1 plus, it's not plus, it's minus, because I'm going to pull everything to the y's on the other side, minus 1.4 z to the minus 1 plus 0.45 z to the minus 2, that's y of z, equaling 1 plus 1/2, 1 is scaled by z to the minus 1, plus 1/2 z to the minus 2 u of z. So that g of z, the system, is now y of z over u of z is now equal to z to the minus 1 plus 1/2 z to the minus 2, all divided by 1 minus 1.4 z to the minus 1 plus 0.45 z to the minus 2. And if I wanted those in terms of powers of z, positive powers of z, I would multiply both numerator and denominator by z squared. Downstairs I have z squared minus 1.4z plus 0.45. and upstairs I have z plus 1/2. I know you can see that the denominator actually factors into that. That's the and you could do the quadratic formula, you could see it, or you could just find the roots of that quadratic. And they actually end up being a pole at 0.9 and a pole at 0.5. What's the natural or homogeneous solution or structure? And is the system stable? The system is stable because those both have magnitudes less than 1. So if we just wanted the natural response of our system, or the homogeneous, we would say, oh, it's going to be some multiple of 0.5, that's the mode to the n, plus some other multiple times 0.9 to the n greater than or equal to 0. If I just hit this with some initial conditions, this is how it would move. I'm not asking you to find the alphas because I say what's the structure. The particular solution structure is determined by the excitation, and that's determined by this. And generically, I'm going to have a cosine and a sine because they're going to be shifted relative to the origin. So now if I said the particular solution, and this is the response due to the forcing function, then that is y sub p of n is equal to beta 1 0.7 to the n cosine pi over 8n plus beta 2 0.7 to the n sine. And what's the total structure? It's the combination of the homogeneous and the particular. And generically, I'm going to just say that that has different coefficients. What was it? 0.9 plus the y sub p of n. Beta 1, and here I'm getting lazy, so I'm going to say beta 1 hat 0.1 to the n cosine pi over 8n plus some angle, gamma. That accounts for the other sinusoid. There would be my generic structure. I needed my natural modes. I needed my modes due to the excitation or the forcing function. I combine them. There's my structure of the response. Is what? Theta 2. I don't even see a theta 2. Alpha. So alpha, I can bar that as well. So alpha bar, yes. So that should be an alpha 1 bar and an alpha 2 bar, since I'm distinguishing those from the original alphas. And I think I'm out of time. And I'm going to try to post this. Thank you for your patience, your dedication, and your endurance.